Hello everyone, welcome to this video. In this video, we have to show that in a finite group, show that the number of non-identity elements that satisfy this equation x raised to power 5 is equals to e is a multiple of 5. So in the question they are asking about multiple of 5, but I think it should be a multiple of 4. Let's proceed and see towards our answer in order to solve this question. So first of all, if we suppose G as some group which is a finite group, so it would have n suppose n elements within it and its order is n. Now let us suppose A is some element which is a member of G such that it is not equal to identity, and moreover it satisfies this condition that a raised to power 5 is identity, right? Now we need to show that what all other members of this kind would be there which satisfy this property, and they must not be an identity element. So let's check for a square. If you have a square, now you know the properties of exponents. If you have a raised to power m then raised to power n, it is equals to a raised to power mn, and it is further equals to a raised to power n then raised to power m. So if we use this thing over here, a square raised to power 5, it would become a raised to power 5 raised to power 2, right? Now what is this? Because we are given this condition for a, this thing we have assumed to be true, correct? If this thing is true, then we would have this as e square, and what is e square? It is e, correct? So that means this a square also satisfies this condition. What about a cube? A cube, if you see, using the same property, it also satisfies the same condition, and a raised to power 4 also satisfies this condition. Now we have found 3 elements which satisfy this condition. Are they also non-identity elements? We need to check this thing. So if we check this thing, so first of all, let's check whether this is identity or not. We say it is not identity. We claim that they are non-identity elements. How? Let's see that from here. If this is an identity element, if a square is identity, we know we have this condition, a raised to power 5 is equals to e. This is given to us. So if we combine these two conditions, we have a, you can write a raised to power 1 as a raised to power 5, a square raised to power minus 2. So it becomes a raised to power 5, a raised to power minus 4, which is a raised to power plus 1, right? Now here we are using what identity? We are using a raised to power m into a raised to power n. It is a raised to power m plus n, correct? So this becomes a. So when you simplify this, what is the value of a raised to power 5? Using this condition, we have this as equals to e. What is the value of a square? We have assumed this to be e, right? So it is e raised to power minus 2. So when you simplify this, you would have again the value as e, right? So your a comes out to be equal to e. However, this is not possible because in the very starting we have assumed that a is a non-identity element. Hence this is a contradiction. Hence this thing cannot be true. If this thing cannot be true, then we have this thing as true, which is a square is not equal to identity element. Similarly, a cube and a raised to power 4, they are also not identity, because if a cube is identity, then together with this expression we would again get a as equals to e. How? Because you can write a raised to power 1 as a raised to power 1 could be written as a raised to power 6 minus 5, which again could be written as a raised to power 6, a raised to power minus 5, which could be written as a cube square, and it could be written as a power 5 raised to power minus 1. So this is what I have written to be here. Now you know the value of a cube. What is it? It is e, right? The value of a raised to power 5, it is also e using this expression. So substituting the values, you see that your a comes out to be e, which is not possible because a is the non-identity element. Hence this thing a cube is also a non-identity element. What about a raised to power 4? If a raised to power 4 is identity, together with this expression, which is the given condition, right, we are now able to write a raised to power 1 as a raised to power 4 plus minus a raised to power 4 plus 5. So it could be written like this. So you can write a raised to power 4 whole raised to power minus 1 and a raised to power 5 like this. Now you can substitute the value of a raised to power 4 as identity, right, and a raised to power 5 as identity, so that you again get a is equals to e, which is not possible. Hence this case is discarded. Hence we have a raised to power 4 also as not equal to identity. Hence we obtained three numbers apart from this a. We obtained a square, a cube, and a raised to power 4 as non-identity elements which satisfy this condition. If that is so, that means the number of non-identity elements in a finite group G which satisfy this condition is a multiple of 4. So that is why, according to me, in the question here they should have written multiple of 4 instead of this 5, right? Okay, moving forward on to the second part. In the second part, they are saying if the stipulation that the group is finite is omitted, that means if we remove the condition of finiteness of this group, that means if we suppose that our group is infinite, its order is infinite, so that means it would have infinite number of members within it, then what can we say about the number of non-identity elements which would satisfy this condition? So let's see what would happen here. In the second case, let's discuss if our group G is infinite, then in that case we could have two possibilities. In the first possibility, we would have our group G as cyclic group, and in the second case, let's take this to be non-cyclic. If it is cyclic, then the number of elements of G such that this condition is satisfied is only satisfied by the identity element, because when you take any other power of the generator, you would generating whole of the elements of this group G. Right, so therefore in this case we have only the identity element which satisfies this condition. Hence no non-identity element exists in this case, and hence we have 0 such members. What about the case of non-cyclic group? If when G is non-cyclic group, then the number of such elements would be infinite, right? Why infinite? Because this would be the generalization of our first case, because in this case we are saying the number of elements, they are not equal to 4, but we are saying it is a multiple of 4. What do you mean by multiple of 4? Multiple of 4 means if you take their powers, a square raised to power something, a cube raised to power something, a raised to power 4 raised to power something, it would again become e. So if you take the powers of a square, a cube, and a raised to power 4, you would again get the identity element, and moreover these are not the identity elements. So because as such now we do not know what is this number n, so depending on this n, you would have the multiple of 4 as the non-identity element. So it could either be 4, it could be 8, it could be 12, it could be 16, and so on. This number could be like this, right? And if this would be stopped somewhere if you have finite group, and it would proceed likewise. You will have infinite multiples of 4 in the case when you have infinite members when it is a non-cyclic group. Hence in this case we have infinite such members. Therefore when the group G is infinite, then the number of non-identity elements, they could either be 0 or infinite. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.